Hi everyone. So this is again a continuation of the transient response or transient analysis of integrators and differentiators. So just to remind you guys, when I'm performing the analysis of these circuits, I'm assuming the op-amp to be ideal, and the only non-ideality is that its output can saturate to plus minus 15. So here its DC gain is assumed to be infinity, its UGB is assumed to be infinity. Okay, that's the assumptions that we are making here. It's a very simple saturating non-ideality that we have considered here. Now once I finish the discussion of frequency response of slightly more complex op-amp based circuits, integrators, practical integrators and differentiators, then we'll try to draw the transient response for those circuits, including the op-amp's UGB taking the op-amp's UGB into account. That will be a little bit more complicated, but we will slowly build one by one, the idea by idea, before we reach to that stage. Okay, so as always, remember guys, analysis is just to give you an understanding. How to understand and interpret these op-amp based circuits. It's very helpful because when you're, let's say, as a circuit designer, you go on to build amplifiers in the future, or you are analyzing any analog system. It can be even in sample and hold circuits in ADCs, or some loop filter circuits in PLLs and analog PLLs. You may encounter such scenarios, and that's why these analysis techniques will be useful. Okay, if the circuit becomes too complicated, of course you have to rely on circuit simulators, but we can still reduce that to a good extent to a simpler model and predict or understand and interpret those behaviors. So that's why we are carrying out all these analysis. Okay, so we'll start with the problem. So the circuit given to you is a simple ideal inverting integrator. A step input is applied to the circuit. The step magnitude is delta V. In this problem, delta V is given to be 10 volts. And the RC time constant of the integrator is 1 millisecond. Okay. And the saturation limit voltages are plus minus 15 volts. And the initial condition for the capacitor, it's given. You have to solve it for two different cases. In one case, look at the polarity of the voltage. The positive plate is the output connected to the output node, and the negative plate is connected to the inverting terminal. So VC of 0 minus, we have to first assume it to be 0, and then we have to assume it to be plus 5 volts and solve this problem. Okay, so first we'll assume VC of 0 minus is 0 volts. So if you guys recall from our previous lecture, if VC of 0 minus is 0 volts, and we are assuming at t equal to 0 minus, for t equal to 0 minus, the step hasn't arrived yet. So the circuit, the input, the voltage at this node is 0 volts. No current flow through the resistor. So therefore, this node will be at 0, and output node voltage V naught of 0 minus will be at VC of 0 minus. Okay, V naught of 0 minus will be exactly equal to VC of 0 minus, and that will be, in this case, it's given to be equal to 0 volts. So we know the initial output voltage, and that is simply equal to 0 volts. Okay, so this directly follows from our discussion in the previous lecture, and I'm just quoting the result here, and or even otherwise you can easily see that the output voltage will simply be equal to V naught of 0 minus will be equal to VC of 0 minus, which will be 0 volts. Now comes the moment, that is at t equal to 0, a sudden step input is applied to the circuit. The moment you apply a step input, the capacitor will act like a short circuit. Remember, it will not, when I'm using the word short circuit here, to simply say that the voltage across a capacitor cannot change instantaneously. Which means at that switching event, it will act like a fixed voltage source. If the initial charge stored across the capacitor is 0, then it will act like a short circuit. So I have to be careful. So that's why I have written this. The voltage across the capacitor cannot change instantaneously. What does that mean? It means it's going to act like an ideal voltage source. So I'm replacing the capacitor by an ideal voltage source of value VC of 0 minus. So VC of 0 minus should be equal to VC of 0 plus. So when the switching event is happening, and remember, this is the capacitor voltage can change instantaneously, provided there is some kind of an impulse current, right? If there is an impulse current in the circuit, yes, it can change instantaneously. But in this circuit there is no scope for any impulses. You are applying a step input to the resistor, so there can be a large value of current, but still, for the voltage across the cap to change instantaneously, you need to supply a sudden impulse of current. That's not possible here. So we can treat the voltage, the capacitor, like an ideal voltage source in this time interval, 0 minus to 0 plus. So what do I mean by ideal voltage source? I'm simply assuming Vc of 0 minus equals to Vc of 0 plus. So the voltage will not change. Now suddenly there is a DC feedback. There is a negative feedback in the circuit. So that is another point to keep in mind. In integrator circuits, you will have a transient feedback. Okay, especially ideal integrators. Ideal integrators don't have DC feedback in the steady state. There is no negative feedback in the steady state, but they will have negative feedback in at the transient events. Suddenly when you apply a change, the circuit will have negative feedback. So now there a circuit comes into negative feedback, and Vx will exactly become equal to 0, and V0 will be equal to V0 of 0 plus will be equal to Vc of 0 plus, which is nothing but Vc of 0 minus. So the instant step is applied, Vx comes to 0. Vx was already at 0 to begin with. It will stay at 0, but now there is negative feedback in action. Okay, previously cap was open, there was no negative feedback, but now there is negative feedback. From that moment onwards, now I can, at t equal to 0 plus, I can replace the circuit, I can just treat this capacitor will start acting like 1. The voltage can change slowly, incrementally, because the inverting node voltage is at 0, and there is a step voltage of delta V that is applied to the circuit. So a finite current will flow through the resistor, which in turn will flow through the cap, and therefore the cap voltage has to change. Now this is an integrator circuit. We have already analyzed an integrated circuit. Your output voltage is given by minus 1 by RC integral Vi of t dt. Okay, so I'll assume 0 to t, because step input is applied at 0 at t equal to 0, and the initial voltage at the output, ideally the integral should be written this way, initial voltage of the output voltage plus this integral due to the input. Okay, the integral term due to the input. But since V of 0 minus is 0, I'm ignoring that, and I can simply write this expression as minus 1 by RC Vi of t dt. Vi is given to be delta V, a fixed voltage, so V0 will simply be equal to minus of delta V by RC times t. Further in this example, it's given delta V as 10 volts, so it will be 10 by RC times t, which means the output is now decreasing with a slope. It's decreasing like a ramp signal, and the slope of the ramp signal is minus of 10 by RC, which means the output will decrease by 10 volts in one time constant. If time constant is 1 millisecond, in 1 millisecond the output would have decreased by 10 volts. So here I am showing the output graph. The output starts at 0 because the initial capacitor voltage is 0. It starts at 0. Then it starts decreasing with a slope of 10 volts per millisecond, minus 10 volts per millisecond. So t equal to 1 millisecond, it would have reached minus 10 volts. And at t equal to 1.5 milliseconds, that is 3 by 2 time constants. The 3 by 2 time constants, it would reach minus 15 volts. At this point, we have reached the saturation voltage. Now even if you inject any current into the capacitor, the output voltage cannot change. Delta V0 becomes equal to 0. If delta V0 is 0, then there is no feedback in the circuit. Okay, even if you are injecting current, there is no change in the output. Therefore, if there is no change in the output, there will be no change in the inverting terminal as well. So at that point, delta Vx becomes 0. So therefore, I can simply say that the circuit is no longer in negative feedback. Once the output saturates, your op-amp will no longer be in negative feedback, because your op-amp's gain you are reaching the saturation point, and at that point, the op-amp's gain becomes 0. If the op-amp's gain is 0, there is no negative feedback, right? Feedback depends upon A times beta, even though there is a finite feedback factor, right? A is 0, so there is no negative feedback in the circuit. Loop gain becomes 0, so no negative feedback. So just before negative feedback, which is, so we have now analyzed the circuit for the time interval 0 plus to 3/2 time constants, 1.5 time constants. In this interval, the output will just ramp down from 0 to minus 15 volts with a slope of minus 10 volt per 1 millisecond. Vx, the inverting terminal, will always stay at 0 volts. So far, it has been staying at 0 volt. See, previously in the steady state, it was staying at 0 volt. Okay, even though op-amp was out of, there was no negative feedback, but because the input was 0, this node was also at 0 volts. Okay, so at this point, the inverting node's voltage can depend upon the voltage you apply at the input, the steady state voltage you apply at the input. But since that is 0 in this case, you are applying a sudden step which goes from 0 to delta V. So your input was 0 before t less than 0 minus. Before the switching event, your input was 0. Therefore, Vx was 0. Now, after this event, there is negative feedback present in the circuit. After the 0, if you see here, the output Vx is exactly equal to 0, and that is forced to be equal to 0 by the action, by the negative feedback action. And this here I'm going to call it virtual ground. At this point, it is acting like a virtual ground. It is exactly tracking V plus. V minus, which is Vx, is exactly tracking V plus. Okay, so, and it has been 0 till the output reached minus 15 volts. From then onwards, once the output reaches minus 15, your op-amp's output voltage cannot increase any further. It will stay put at minus 15 volts and it will keep supplying whatever current the circuit demands. From that point onwards, I can simply remove the op-amp. There is no negative feedback anymore. So the circuit simply becomes, the op-amp is no longer in the picture. It will just act like a DC voltage source of value minus 15 volts. Now there is only an RC circuit in the picture. So we end up having a situation like this. See, the output voltage is at minus 15 volts. Vx is at 0. So therefore the capacitor voltage at 3/2 time constants will also be exactly equal to minus 15 volts. So that's what I've shown here. This is the model of the op-amp. Op-amp, I'm just replacing it as a fixed minus 15 volt DC source. Capacitor has been initially charged to, capacitor is charged to minus 15 volts at the end of 3/2 time constants. And then you have a resistor and 10 volts at the input. Delta V here is 10 volts. Okay, it's a step input. So after the switching event, we are looking at the for t greater than 3/2 time constants, it is a 10 volt input. Now this is a first order circuit. This we have already analyzed it to death. We know very well how to analyze first order circuits. Anytime you are given a first order circuit like this, if you want to find any node voltage, you need to know the initial voltage and the final voltage and the time constant. If you know these three, you can easily plot any node voltage. So the only unknown node voltage here is Vx. I need to find what the node voltage of Vx here is. So I'll start. Initially Vx was 0 volts, right? Vx at 3/2 time constants was at 0 volts. Now, because of this RC charging, it can either increase or decrease, and by inspection we can quickly see. You can either apply principle of superposition and find out what will be Vx, or you can see any RC circuit. If you have an RC circuit with some DC inputs, the steady state is achieved when the current in the circuit goes to 0, right? At that point, capacitor voltage would have reached a finite value. Capacitor will act like an open circuit in the steady state, so the current would have reached 0. For the current to become 0, the condition here is Vx should be equal to 10 volts, right? Both the voltages of the resistor should become equal. So the terminal voltages of the resistor should become equal to 10 volts and 10 volts. Then the current in the circuit becomes 0. Okay, now it's a very simple problem. So Vx starts off at 0. We know the final value is 10 volts. And there is only, since it's a first order system with a single RC time constant, the output will raise, so the node voltage Vx will start at 0 and it will undergo a first order RC charging, and the final voltage it will reach is 10 volts. So Vx, the op amp's inverting terminal, will finally go to 10 volts. Remember, I have assumed the op amp to be an ideal voltage source of minus 15. This is true as long as your input differential voltage is less than 0. Now what is your input differential voltage? Which is simply V plus minus V minus. V plus is 0 volts and V minus is Vx, and Vx, I have plotted this. So Vx starts at 0 and reaches 10 volts, and therefore minus of Vx will always be less than 0. So Vd is always less than 0. Therefore your op amp's output will stay put at 15 volts, minus 15 volts. It will always stay at minus 15 volts. Okay. So now you know the op amp's output voltage, which is at minus 15, and you know the inverting terminals voltage. You can easily plot the capacitor voltage. You just have to subtract the two. Or you can directly plot the initial voltage across the capacitor is minus 15. The initial voltage across the capacitor, that is at this point, we are at minus 15. This is the capacitor voltage, and the final voltage across the capacitor happens to be when this node would have reached 10 volts. So this node is at minus 15 volts. The other node is at 10 volts. So the total voltage across the capacitor will be minus 25 volts. So which means it starts off at minus 15 and then reaches minus 25 like a first order circuit. So it will go like this. So the capacitor voltage will start reaching minus 15. After this point, it will reach minus 25. Okay. So that's how the capacitor voltage will look like. See, before this point, before the output is saturated, if you see this Vc of t, the capacitor voltage was exactly equal to the output voltage. But once your output voltage is saturated, output cannot increase any further. So from that point onwards, your capacitor voltage Vc of t will become greater than V naught. Okay, and that follows because it's a first order RC charging. Op amp is no longer active. It's no longer the circuit is no longer in negative feedback. So that's how this voltage will look like. So you can see, once you know the voltage, you can also plot the currents in the circuit, right? If I ask you to plot the current flowing in the capacitor, that is exactly equal to the current flowing through the resistor. You know the input voltage, you know the node voltage Vx, and you can easily predict what will be the current. The current will be some peak, it will reach some peak value. Okay, the current will be a constant initially, and eventually it will go down to 0. Okay, I'll leave that as an exercise. It's very simple. Delta V by R will be the current in this interval. When the output is charging, inductor's output is charging, the resistor is supplying a constant current of value delta V by R. Okay, from this point onwards, after this, the resistor voltage across the resistor comes down to 0, which means current also will go down to 0 with a time constant of RC. This is how the current waveform will look like, or the voltage across the resistor. Okay, so all these things you will be able to draw or interpret. The second case, we'll assume what happens if your capacitor voltage is finite and it is equal to 5 volts. It's very simple. You can use the same analysis techniques and solve this one as well. It's not different at all. You can start off with a circuit. What happens for t less than 0 minus, that is, or t equal to 0 minus. So Vc of 0 minus is given to be 5 volts, and the input voltage is initially 0, right? It's at 0 volts. It's a step input. So initially it was at 0. No current is flowing through the resistor. So this node will be at 0. So your output voltage Vc of 0 minus will be equal to 5 volts. Now suddenly you apply the step input. When you suddenly apply the step input, your capacitor will act like a DC voltage source. Your cap will act like a DC voltage source. I can replace this cap as a DC voltage source of value plus 5 volts like this. There is negative feedback. Okay. The incremental resistance will be 0. So that's what I mean by capacitor acting like a DC source. So there is negative feedback, and this will act like a 5 volts. This node will be at 0 volts. So output will be at 5 volts and this will be at 0, and now you are applying a step of 10 volts. So you can use all the same analysis as before. The only difference is instead of output starting at 0, it starts off at 5 volts. From 5 it will keep on decreasing. So the equation for the output will look something like this. It will be V naught of t for t greater than 0 plus will be minus of 10 by RC times t plus V naught of 0 minus, and this was 5 volts, so it will start at 5 and decrease. Remember, it will keep on decreasing at the slope of 10 volts per 1 millisecond. Okay, 10 volts in one time constant. It will keep decreasing in this with this slope. So for your output to saturate, it has to go to minus 15. You are starting at plus 15. So the total change in the voltage is 20 volts. So your output has to go from plus 5 to minus 15. So which means the net change in the voltage is 20 volts. If your output is decreasing at the rate of 10 volts in 1 millisecond, to reach 20 volts, you have to spend at least 2 milliseconds. Okay, exactly 2 milliseconds. So in 1 millisecond, if you start from 5, your output would have decreased by 10 volts. So your output will reach minus 5 volts. In another millisecond, another 10 volt decrease, you will reach minus 15 volts. So previously, if you guys recall, we had output was saturating just at 3 by 2 time constants. Okay, that was 1.5 milliseconds. Now it's saturating at 2 milliseconds. Okay, so keep in mind all this while as the output was going from 5 to minus 15, the op amp is perfectly in negative feedback. And if you look at the transfer characteristics of the op amp, see the op amp's transfer characteristic looks like this. All this while Vd was 0. The differential input to the op amp is 0 because op amp is a negative feedback. Vd is 0. So the output of the op amp goes from, I'm drawing this transfer characteristics. It goes from 5 volts all the way till minus 15 volts. Vd has been 0 all throughout this transition. Okay, that is Vx has been 0. Your Vx has been 0 throughout this transition till this point. Now after the output saturates, the capacitor has reached a voltage of minus 15 volts. See, it started off at plus 5 and now it is charged to minus 15 volts. Now we are back to what we were in the previous example as well. Once the output is saturated, the circuit reduces to the same circuit after it saturates. Negative feedback is no longer present because the op amp's incremental gain is now 0. So therefore no negative feedback, and so we know how to solve this circuit. So Vx eventually will come to 10 volts because the input is at 10 volts. So this will eventually come to 10 volts so that the current in the circuit is 0. Cap will act like an open circuit, and capacitor will steady state. The voltage across the capacitor will be 25 volts, minus 25 volts. Okay, so that's it. So the only difference here is the initial starting point. As far as Vx is concerned, it will remain the same as it was in the previous case. There is no change there. It will stay at 0, and once the output saturates after 2 time constants, it will raise with a first order time constant. It will increase like a first order response and finally reach 10 volts. The voltage across the capacitor starts off at plus 5. Okay, starts off at plus 5, reaches minus 15 in 2 time constants. From there it undergoes a first order charging to minus 25 volts. Same as before. So I'm quickly drawing this because I've already explained this in the previous problem. Okay, the only thing is it's going to initially the saturation was happening just at 1.5 millisecond, which is 3 by 2 time constants. Now it happens at 2 time constants. Okay, so initially depending on the voltage across the capacitor, that transition can happen. That saturation point can happen anytime. Okay, so if I say the initial voltage across the capacitor is minus 15 volts, what do you think will happen? Can I say that if I say the initial voltage across the capacitor is minus 15 volts, what do you think will happen to the circuit? It's the same circuit, and it's given that the initial voltage across the capacitor is minus 15 volts. And now you are applying a positive step, say 0 to 10 volts. What will happen? Yes, so the output is already saturated. It's already at plus 15. Okay, since it is already saturated, even though you apply a step input suddenly, this op amp will be in open loop. There will be no negative feedback, and the op amp will act like a DC voltage source of value minus 15. Okay, Vx was initially at 0, 0 minus. So the same things will happen. Vx will rise from 0 to 10 volts, and the capacitor will initially it was charged at, it was, remember, the capacitor's initial voltage is minus 15 to begin with. So at t equal to 0 minus, it will simply undergo a first order charging and reach a voltage of minus 25 volts. Minus 25 volts starting from minus 15 volts. It will gain an extra 10 volt of charge. Okay, and that's it. So if you see, right, the circuit was already saturated to begin with. It didn't take much time, and then when we applied a step input, even though the cap acted like a voltage source, the op amp, since the output was saturated, op amp, there was no negative feedback in the circuit. So the output, the capacitor voltage output stayed at minus 15. Okay, output will stay at minus 15. The capacitor voltage will start off at minus 15 and then decrease to minus 25 volts. This is what is supposed to happen. And Vx, this node voltage Vx will start off at 0 and go to 10 volts. Okay, so this is about how to analyze RC integrator circuits. The next lecture, we will analyze a very similar problem. It will be an RL integrator.